Hello, everyone. Welcome to NC-CAV seminar. We're excited that everyone's here today. We have an excellent speaker, Mr. Farabi, who will be speaking about using connected autonomous vehicles as mobile traffic controllers and roundabouts. A little bit about him is that he is a transportation systems researcher who specializes in developing advanced control algorithms to enhance urban mobility. His work integrates operations research techniques with traffic engineering to optimize traffic operation and mitigate congestion. He's currently pursuing a PhD in civil and transportation systems engineering at NC State University. He also holds a master's in operations research from the same institution. Mr. Farabi has contributed to urban congestion management by leveraging vehicle to everyday connectivity to design innovative traffic management solutions and autonomous vehicle control strategies. He has published and presented his findings at multiple prestigious conferences, including the Transportation Research Board annual meeting and the Informs annual meeting. So I'm very excited to welcome the speaker, and I will pass it off to you, Mr. Farabi.
Thank you, Christina, for the nice introduction. So good afternoon, everyone. I'm so happy to be here and see a lot of audience here in the Friday afternoon. So the research that I'm going to discuss is on using connected autonomous vehicles as mobile traffic controllers in roundabouts. So this research is done by me and by my supervisor, Dr. Ali Hajbabai, Associate Professor at NC State University. So for the presentation, I would love to have it interactive. So feel free to ask any questions in between if you have, and I will love to answer them. And yes, that's pretty much it. And I think I should start the presentation. I think you all can see my screen.
Yes.
That's great. So at the very beginning, I would like to discuss what roundabouts usually offer if we compare with signalized intersection. So roundabouts offer improved safety. It has lower number of conflict points if we compare to signalized intersection, and it operates under low speed. In fact, Federal Highway Administration considers roundabout as one of the safety countermeasures, as it reduces the fatalities by 90% and injuries by 75% if we compare with signalized intersections. So apart from the safety benefits, from a cost side, roundabout, it does not require any signal control hardware. So we have low electrical costs and low maintenance cost. So overall, roundabout has a lower operational cost. It can operate even during a power outage. So we have all seen if there is a power outage, signals don't work. So we need law enforcement or police officers to operate, but roundabout can operate there greatly. Having all those benefits, roundabouts is suitable for low to medium traffic. So they are not good at handling when the traffic demand gets very high. So the reason behind is that roundabout relies on stochastic gap acceptance mechanism of drivers. So this will be much clearer if we look at the example. So we have a scenario where two cars, one is on the circle, another is a blue car that wants to enter the roundabout circle. The hesitant blue car driver, assuming that it will have a conflict with the black car, it yields to that car. But what happens, like we can see at time step 4, the black car just passed by and it never had any conflict with the blue car. The blue car right now decides to enter the roundabout. So this is a pretty common dilemma we see in a roundabout where the utilization of available gaps is kind of inefficient. So such kind of inefficiency increases the wait times of the cars and thereby increases the delay. So if we talk about connected automated vehicles or CAVs, cars which have definitely computing resource, it can communicate, it broadcasts information, it can receive information. So based on so many articles, so these cars are great at communicating and cooperating. They're great at improving the gap utilization, as they can do the communication. Thereby, they have a better mobility. They can ensure better mobility and safety. So this brings our research question, is that how we can use the connected automated vehicles, the CAVs, to improve the traffic flow in a roundabout. So if we had full CAV fleets, all the cars are CAV, so they could like simply communicate with one another and reduce the stochasticity of gap acceptance significantly. So that would be a very ideal scenario. But when we have the human driven vehicles, so any CAV that can operate optimally, if it is stuck behind a human-driven vehicle who is hesitant to enter the gap, so thereby it increases the delay for both the HVs and also the CAVs. So in the left-hand side of the figure, we can see a roundabout circle where one of the cars is yielding to the circular vehicle. It is not sure whether it will have a conflict with it or not. On the sorry, left-hand side, right-hand side. On the right-hand side, we have a CAV which is operating optimally, and if it can pass some sort of guidance or information about its direction, and it can help reduce the stochasticity of the HVs, we can significantly improve the operations of the roundabout. So if we can use the CAVs acting as temporary mobile controllers or temporary mobile controllers, we can improve the roundabout operation at a significant level. Therefore, in this research, we have developed a methodology to optimize the trajectories of CAVs in a roundabout so that we can improve the traffic operations for both the human-driven vehicles and the connected and automated vehicles. The study uses vehicle-to-vehicle and vehicle-to-infrastructure connectivity to control the CAV movements. And at the same time, we use the CAV as mobile controllers to guide the waiting HVs in the merging areas. So I will be discussing mathematical models behind this study. So before I go in there, I would like to discuss some of the key notations that will be coming frequently in the next couple of slides. So at very first, we have the decision variable, the acceleration of CAV at any particular time, which is the AI. We have position of a vehicle and the speed of a vehicle as state variables. We can see all of these are in bold form. So they are like a vector. So it has an X component and a Y component. In sets, we have capital T as the set of all time steps. We have capital V is the set of all vehicles. We use subscript small a to VA to denote the set of CAVs and VH to denote the set of all HVs. We also have VM to denote the HVs that are waiting at the merging areas. Another set is that CIJ, which is also very important, as the set of vehicle pair in the conflict zone that we are going to define. So a set of vehicles that are in the conflict zone is part of that CIJ. In parameters, we have two most important parameters, the R, which is the minimum safety distance between a pair of vehicle, and we have MIJ. So it basically an activation parameter. It turns the safety constant on when there is a need, and it turns it off if the cars are far away and there is no safety requirement. So here's a part of our model formulation. So at the beginning, we have the objective function. So the objective function here has two parts. The very first part tries to maximize the throughput, which basically tries to make sure or push the vehicles to complete their trips. And another part that we have is a driver comfort part. It tries to ensure vehicles acceleration do not deviate significantly. So we want to develop a model where we try to push as many as vehicles out of the system and at the same time ensuring their comfort. Here we have the kinematic constraints. Those are physics-based constraints. Basically, we use them to update the speed and position of vehicles over the time steps. Then we have the initial position and initial speed. So we collect it from our system at any particular time. We have constant 5 and 6 basically for human drivers behavior. So as of now, we are expressing them with a generic function. So constraint 5 represents human drivers behavior in the roundabout. Constraint 6 is a generic function as well. It tries to uh, capture the effect. If a HV gets information, how will it react? So here we have a boundary for both the accelerations and the speeds of vehicles. So we want to ensure the acceleration and the speed of cars do not like go crazy. Here we have the safety constant, and probably the most important constant over here. So between any vehicle pair, we need to ensure a minimum safety distance is there, which is the Rij. We also ensure a sigma ij to deal with the stochasticity. We have the mij, basically a parameter I just showed like one slide ago. So it just activates the safety constraints and deactivates the constraints. So we are going to have a couple of discussion on the safety constraint itself. In constraint 10, we have the planning constraint. So what each car is going to do in the long run, which direction it is going. Then we have a constraint where we ensure position and speed have at least a value of 0. So for the safety constraint, in the left-hand side, we have the routes defined. So we have like 12 routes total that we have considered in the study. And on the right-hand side, we have the conflict zone mapping. So we have 3 colors, green, the complete red, and a yellow color. So if you look at the table, you can see that the diagonal is completely red. So what does it mean is that if any 2 cars that are traveling on the same route, say for 2 vehicles are going using the route 2, so we will always have to do a safety check between these 2 cars. However, if a car is on route 1 and another car is on route 7, so these 2 cars, they don't have any safety conflict because their routes are completely different in different direction. They will never have a conflict at all. So we put them as a green. So the yellow is a time-dependent conflict zone, and majority of is yellow, so which is basically if 2 routes have a portion where they will have conflicts. So this will be much clearer if we show these diagrams over here. On the left-hand side, we have northbound through, which is the route 2. So 2 cars are on that route. So these 2 cars, we will always have to do a safety check. On the right-hand side, we have 2 routes that share a certain portion. So we have northbound right and northbound through. So as long as the cars are in the in the yellow zone or will be in the yellow zone based on the prediction, we will have to ensure safeties. If the cars have diverged, so their paths are no longer crossing, we can simply relax the safety constraint. Similarly, here we have 2 left turning movements. So if we have 2 left turning movements, we have the complicated scenario over here. So 2 particular zone of conflict. So we have to ensure safeties during in that particular zones. Otherwise, we can relax the safety constraint. And lastly, we have the northbound right and the southbound right. These vehicles will never have any conflict. They're in completely 2 different direction. We can simply relax the safety. So the model I have discussed so far, what it does, it optimizes the CAV acceleration decisions, and at the same time, it generates guidance for the human-driven vehicles. So this model is two-dimensional, and therefore it has many nonlinear constraints. So it's very complicated to solve it. We can definitely use any heuristic algorithm, but that would affect the solution quality. Therefore, we brought some techniques to solve the optimization model. So at the very beginning, we simplified the 2-dimensional model using a Frenet coordinate system. So therefore, what it does, it converts the 2D problem into a single dimensional problem. So it you takes the vector form and converts it to a scalar form. So this significantly reduces the complexity of the original model. Then we have the nonlinear safety constraints. So we have to linearize it. So we use that using BigEv method. We have some generic functions for the human-driven vehicles. So we use car following model and at the same time introduce reduced speed area, which I will be explaining later on in the slide, to model the behavior of HVs in the roundabout. And lastly, we have a model predictive control framework to account for any changes in the environment. Here is a quick slide for the Frenet coordinate system. So in Frenet coordinate system, positions are measured from an origin and distances are simply measured along the center line of the road. So in the right-hand side, we can see if we use the Cartesian format. So we have to take the X coordinate and Y coordinate to get our safety distance. So which is nonlinear. So it's a bit complicated for the optimization model to handle. However, if we use the Frenet frame, we can simply just calculate and deduct the positions from position of car 1 to car 2. So which is pretty much easier. So if we transform the optimization model using our Frenet transformation, we can simplify the model. So this is almost the same as before. Its objective is maximizing throughput while minimizing acceleration variation, but all these variables, they are now scalar. And if we look at the safety constraint, it also is a scalar, but one change is there is that we have a term epsilon ij in the model. So this is something new that wasn't in the previous constraint. So what's the reason for bringing that epsilon ij? So when we convert the model using Frenet frame, positions are no longer unique. Two cars that are at two different origins traveled maybe 4 meters, but they are essentially same to the model. So think about one of the scenario in the figure. We have a conflict point. So the white car can reach the conflict point maybe traveling 80-meter distance, while the black car over there, it can reach the same point traveling 120 meters. So at a particular time, if we simply look at the position, so we're going to consider the model is going to consider the position has like a 40-meter difference. However, they are in the conflict zone. So we somehow have to ensure the positions when we are calculating the position difference, we take account for that. So we have introduced a relative distance parameter epsilon ij in the safety constraint so that the positions are comparable and we can ensure the safeties. So based on the previous slides and discussions, we usually end up with 4 sets of safety constraints. The very first one is constraint 20. We don't have any epsilon because all these cars have the same origin, but we have to do the safety check. It is same when that two cars shares the same origin. So there is a part of the route that has conflict zone, which is the yellow portion over here. Another one is like when the cars are completely out, we do not need any safety check, and we also do not need any epsilon ij here. Then we have the complicated scenario when we have the epsilon ij because we have to calculate the positions there from different origins, and at the same time, sometimes we need to do the safety check. Sometimes we can simply relax it during the green time. So the conflict zone mapping parameter MIJ, we estimate it based on the current position and current speed at any particular time. I have already mentioned I use a BigEv method to simply linearize the safety constraints. So constraint 24 to 26 is basically the linearized version of the safety constraint. Right now, modeling the HV behaviors, we somehow have to predict the HV motion. So therefore, we use Haley's car following model to do that. So constraint 27 and 28 is basically Haley's car following model. It takes the lead vehicle and the follower vehicle's speed and lead vehicle's position and follower vehicle's position to calculate the acceleration. Other than that, we have a reduced speed area constraint. So this is basically due to the fact that even if under a very low traffic, say for example, an HV has entered the roundabout, approaching the roundabout circle, it has to look for gaps because it is not sure like whether it will have a without any conflict free gap or it will have a conflict. Therefore, it reduces the speed. So we are accounting for such a behavior using constraint number 29. And constraint 30 and 31, same as before, just ensures non-negativity. Here is the schematic diagram of the model predictive control framework. So it has a couple of modules that I'm going over. So at first, I have the simulation model. So we use micro simulation, we use the PTV VSIM to code our models. So our roundabout is there. So it generates traffic, it creates a roundabout scenario. So what we do is we collect the position and speed of cars from the roundabout at any particular time step, and we pass those information to our next module. So in this module, what we do, we simply transform the positions into Frenet frame, and we also do the mapping for the conflict zone, which is essentially needed for the safety constraint. So when we have transformed our position, we have mapped our conflict zone parameter MIJ, we simply pass it to our optimization module. So optimization module takes those values and optimizes and therefore generates two sets of decisions. One is the optimal CAV states, which is the acceleration, optimal CAV behavior, and at the same time, we have optimal control guidance for the HVs, how an HV should react, whether it should enter the roundabout or not. After having those decisions, we simply send those decisions back to the main simulation model for implementation. And we keep doing that in a way so that we generate the decisions, we implement it, we again look at the system about in the next time step, again do the optimization. So we keep following this model predictive control framework until we reach the study period. So quick look at our parameters that we have used in the study. So time step duration is delta, which is 0.5 seconds. Then we have maximum speed, 40 kilometer per hour. I think that's 25 mile per hour. Our prediction horizon, we have used 8 time steps to 16 time steps. That is basically like 4 seconds to 8 seconds. And our maximum acceleration, 4 meter per second squared. Deceleration, the same in negative. And that's pretty much it over here. So I can talk a bit about the case study. So we have selected a single lane roundabout from Raleigh, North Carolina. So we did two scenarios using that simulation model. Firstly, we did mixed traffic simulation based on highway capacity manual. And we have compared our performance, which is the proposed control, with the mixed traffic simulation. Couple of demand plans we have used, starting from 400 vehicle per hour, we went up to 900 vehicle per hour demand. We also have one asymmetric demand plan. So which is in one direction, we have 600 vehicle per hour. In another direction, we have 300 vehicle per hour. And the analysis period for our study was 15 minutes. We have multiple CAV penetration rates starting from 0%, which is plain HVs, which is the conventional operation. And with 20% increment, we went up to 100%, which is like the full CAV fleet. Our analysis runs included 70% through movement, 15% left turning, and 15% right turning movements. We calibrated our simulation model. So we basically checked for car following parameters and gap acceptance parameters for our benchmark. So it matches the highway capacity manual capacity values. So here is a two penetration rates. Sorry, here is like a comparison of our model calibration with the HCM value. So we took two CAV penetration rates as for example. So you can see that the simulation and the HCM is quite a bit of matching. So basically the deviation we found is less than 5%. So basically why we brought this up is to compare our proposed control with a model that's has a more valid basis.
What is HCM?
HCM is the highway capacity manual.
Thank you.
Sure. So here we can see some animations. So on the left-hand side, we have conventional operation with CAVs as per the highway capacity manual. And on the right-hand side, we have our optimized operation. So this is for a demand level 900 vehicle per hour. So it's pretty high demand. So we can see long queues that are forming on the simulation or the conventional operation. But if we can optimize the vehicle movement and use our control methodology of mobile control concept, we can see that the cars can move, they can talk to each other, and they can have like a very smooth operation and significant low gap acceptance time. So another thing is that you can see the number of cars on the circles. In conventional operation, it has a lower number of cars on the circle, but in optimized operation, we have much higher. So similar to other animations where we have 60% CAV fleet on the left-hand side, and on the right-hand side, we have 60% CAV fleet as well for the optimized operation, where we are doing some form of guidance to the human-driven vehicles to accept lower gaps. So same as before, we can push many vehicles into the traffic circle, and at the same time, we can process much larger number of vehicles with the optimized operation. If we compare with the simulation where vehicles are yielding and taking much longer gap acceptance time. Okay. So if I move into the results, so a lot of numbers, I'm not going to go like discuss all of them, but in any performance measures, like whether it's travel time, average delay, average speed, and throughput, using the proposed control, we can significantly improve the conventional operation. So as for one example, I have just put the average delay, so 5 seconds per vehicle in a low demand, which is the 400 vehicle per hour, but even we can drop our delay quite significantly if we keep using the mobile controllers. We keep using the CAVs as mobile controllers, and at best, it can drop like almost like 0.1 seconds in 100%. And the trend is like keeps on decreasing for the delay. We see the same trends for travel time as well. The speeds also increase as we have more CAVs into the system using the proposed control. The throughput goes high as well. Here we have the 900 and the asymmetric demand. The same as before, we see the similar trend here. The travel time, we can see a lot of improvements in travel time and delays, also in the speed. So one example I brought here is the throughput. We can see in conventional, we have 600 vehicle per hour throughput. But if we use the optimized operation, the number of cars that completes the trip increases, and at max, it can go up to like 870 vehicles. We can increase the throughput by quite a good percentage. So here is the same like two graphs I have taken from the table for better clarity. It's quite clear for the demand level 600 that the delays drops if we have more CAVs. It's true for both the simulation and for both the optimization. However, with the optimized approach, we can drop the delay quite significantly. So in simulation with 20% CAV, we have like a delay around 15 seconds, but with the optimization, it's around like 5 seconds per vehicle. Now, if we look at the demand of 900 vehicle per hour, so right now what we can see is that even with higher CAV penetration rate, the conventional operation could not drop the delay because it's a very high demand and it's a bit congested. So we can see the average delay is almost 35 and more than that. But if we use the optimized operation, optimizing the CAV trajectories and also as well as providing some guidance to the human-driven vehicle, we can drop the delay quite significantly. And at the same time—
Can I ask you a question?
Sure, definitely.
Yeah, well, what do you mean simulation versus optimization? Simulation, I mean, optimization is part of your simulation. And how do you distinguish one from the other?
So
I mean,
in
simulation is completely at random. Is that what you're telling me, or what?
the simulation is the highway capacity manual based, the calibrated model that we are running. And with the
An optimization?
is our proposed control, like how we want the system to work. Like we are controlling the trajectories of CAVs and at the same time providing some guidance to the human-driven vehicle. So basically both are done in the simulation as well, but one is the conventional operation, another is the proposed control.
Maybe it is better because it is right now misleading.
I get that. The
Both
term
of
is
them,
simulation because, yes, I get your point. Exactly. I
Okay.
agree. Yeah, it should be like, I think the letter one or title like conventional operation or something probably that fits better.
Okay.
They're saying simulation, yes, because optimization, because we are doing the visualization and simulation as well.
Thank
I
you.
agree with your point. Thank you. That's a great observation. So here we see the delay variation of the human-driven vehicles for a demand level of 900 vehicle per hour. So as what we are doing providing some sort of guidance to the human-driven vehicle. So what happens without the guidance? So in conventional operation, if a vehicle is lucky, it's find a gap, it can enter. So if it in a congested scenario, the chances of getting gaps are quite low. So we can see in conventional operation, which is written as simulation, the delay variation is significant for the human-driven vehicle. Some vehicle may have like a 1 seconds of delay, but others can go up to like 80 seconds or more. So the range is quite high. But with the mobile controller concept, with the guidance from the CAVs, we can drop this delay variability quite at a big margin. So we can see the optimized operation, the delay variation of the human-driven vehicles is quite low. And this range keeps on dropping a bit by bit as we have more CAVs into the system. The more the CAVs we have, the more mobile controller the HVs get. So thereby their delay drops tremendously. Couple of more results. We looked at the approach-wise queue length as well. So in conventional operation, you can see the queues are a bit high. We also see that in the simulation, the animation as well. So the delays in approaches, the queue length in approaches in some cases is more than 50 meters. But with the proposed control, as we are trying to push more cars into the circle, the queue length is much lower compared to the conventional operation. And same goes for the delays as well. So in demand level of 900, we see quite a bit of delays on conventional operation for each of the approaches. In some cases, it goes to level of service of E, or more than that, it can get worse and can become level of service of F. But with the proposed control, the delays are kept under in a much better condition. The trajectories also explain the performances of the proposed control. So in the left-hand side, we can see more zigzags. So it's like more delays for both the human-driven vehicles and for both the connected and automated vehicles. However, with the proposed control, we have a much smoother operation, so we can improve the performance of both the HVs and both the CAVs. As for computation times, it will depend on the hardware or the computation resource, also the prediction horizon, how far do we want to go to predict, and also the solution quality, what sort of optimality gap we are expecting. So in this research, we have used Intel Core i9 processor. We used a prediction horizon of 16 time steps and an optimality gap of 5%. So we can see the runtime variation for 3 demand pattern. So even for the demand level of 900 vehicle per hour, the maximum was around 500 millisecond, but this is for full CAV fleet. So let's look at one of the demand pattern with mixed traffic. here we have an average runtime around 0.35 seconds during the study period. So, but runtime will vary if we have more human-driven vehicles in the system, so their prediction will consume more time for the model. In conclusions, we have developed a control framework that optimizes the CAV trajectories and at the same time guides the human-driven vehicles to enter the roundabout safely. This approach reduces travel time by up to 68% comparative to conventional operation. We also have observed a 44% increase in throughput using the proposed control methodology. And this methodology reduces delay variation as well. So there are some limitations, definitely, like any other studies. We have not considered multi-lane roundabouts. We are thinking of expanding our work to multi-lane roundabouts. And we have talked about a lot of communication. So we haven't really considered the latency or bandwidth or power consumption. So there are some things on that side that we need to be considered if we want to go for implementation. So that's pretty much it. So here is the co-authors, Abdullah Farabi, that's me, and my supervisor, Ali Hajbabai. And lastly, thank you everyone for listening to my presentation. I'm really very happy to discuss more with you if you have any questions, and you can also email Dr. Ali Hajbabai as well. And last, thank you.
Great. Thank you. Any question from the audience?
Very good presentation. Can you go to slide
Sure.
number 36?
Definitely. Yes.
Yeah, okay. This is the trajectory of what? CAVE versus human-driven car. Is that right?
This is on the left-hand side, we have the conventional operation. So HV, we have HVs and we have CAVs. The CAVs have a lower gap acceptance as per the HCM model. So it is like no optimized scenario. So there is no sort of optimization or there is any guidance for the HVs. So cars approach, look for gaps, and they enter. So HVs, as usual, have a high variability. So their gap acceptance like this is stochastic. For the CAVs, they have sort of like information about the surroundings. So they usually have a lower gap acceptance time. On the right-hand side, we have optimized operations. So we have communication, and there is a central optimizer that tells each CAVs, okay, follow this particular trajectory. And at the same time, the CAVs passes some sort of guidance to the human-driven vehicle. Okay, my direction is this, or I'm slowing down, you can accept the gap.
When you say gap, what is that? What does that gap means? It means that the minimum distance between vehicles or what? What do you mean by gap?
Gap can be time and or the distance a car usually can take. So it can be in both forms. So sometimes we use like express as time, like what time. It's like say a circle, traffic on the circle is going to take 2 seconds to reach the conflict point, and that may not be sufficient for a human driver to enter.
Okay. Whenever I go to any roundabout, I think of Dr. Hajbabai. Okay. And this is a very difficult problem, but even this is the starting point for me that I'd like to question if I have time. The pattern that you show here, to me, is a very clean pattern. But when I am in the roundabout, I don't see this kind of a clean pattern because, and also what you have also shown in here is that you have a roundabout that all symmetric. Most of the one that I have witnessed, they are non-symmetric. Instead of having 4 throughputs, we have 5, 7, odd number. Do you see? And then I don't see something because we are human-driven cars. Humans don't have this kind of behavior that you are illustrating in here. We don't, because everybody within a given small amount of time that we have, everybody's pushing the other one either to get out or they're pushing us inside. You see? So
Yes.
I don't know how realistic your simulation patterns are, but let me give you, so taking this as a standard, as a starting point, any optimization method, if doesn't consider human behavior, is going to fail.
Definitely.
What you have in here, both the first minimization and the second as a maximization problem, you didn't consider any human behavior as part of your optimization.
Actually, we do have. So we have
Which one?
modeled the human-driven vehicles. So it's like somehow have to model it. Otherwise, if we don't have human-driven vehicles, you somehow have to predict their movements, like what it is going to be, where it is going to be. So we predict their motion using a model.
So these are your constraint, or these are part of your objective function?
These are the constraints to mimic the HVs or the human-driven vehicles in the roundabout.
Mhm.
So without like predicting their behavior, the system will not work because.
If I may, I'm going to ask one more question and then.
Sure,
Because
definitely.
since roundabout is the time is very short, I am not sure whether information between vehicle and infrastructure gonna help the driver to make a better and informed decision, because the time is really short.
Yes.
So then,
So
how is that infrastructure information gonna help me?
So there are things like if it is self-driving car, so that's a different case. So
Yeah,
it
but
has its own optimized trajectory. So it follows its own pattern. So how the CAVs is doing, it's passing its information to a human-driven vehicle in couple of ways. If it is very congested, so in animation, you could sometimes see that CAVs is slowing quite a bit significantly. It is slowing down to create an additional gap time to let the HVs enter. So this is sort of a forced behavior. Sometimes we can see in roundabout in very congested scenarios. It's like approaching car, sometimes stopping the circulating vehicle to enter. So it's like that dense transition. So here, what we have is a very organized way. Like it's two things: is dynamically adjusting its speed before arriving here, creating an additional time for the human-driven vehicle to enter, and also passing some information that, okay, you can enter. But that passing information either would require a connected human-driven vehicle, so who can receive that information. And if that's not possible, some sort of guidance or communications like we do at unsignalized intersection or at stop sign, we sometimes show our hands, tell the other driver, okay, you go or you move. So for CAVs, it needs some sort of that kind of communications. It requires to adopt. Otherwise, HVs and CAVs in a mixed scenario, we will probably gonna lose or drop quite a bit of performance. So in this study, what we are doing or saying is that HVs, they have the communication capability. That's an assumption, and they're just following it. For a real world application, there will be a couple of issues. As you have said, the short time is an issue. So the CAVs have to behave much earlier before coming to the conflict point. And at the same time, an HV can be compliant or can ignore the decision at all. It decide, okay, this is not safe for me. I don't feel it's safe, so I'm not going to enter. So there would be a compliance issue as well. That needs to be explored. So yes, this is a starting point, and this is like something requires a lot of further studies. I agree with you at that point.
Thank you.
Thank you.
Thank you. So
And
you can hear me?
Yes.
yes.
Okay. So I know that you have been working on a sort of heuristic approaches as well. That's something that you might want to also give us insight on the rationality of moving from this optimization based to heuristic approaches, and the kind of thought process that you end up with that going to the heuristic approaches as well.
Sure. The reason for moving to a heuristic approach is having the runtime issues. So in real world, we will have a lot of more complications. And here in the even in the simulation, when we have like more human-driven vehicles into the system, the higher their penetration rates, the runtimes goes high. So we always have a computational complexity to consider. So to have further efficiency without dropping maybe not significant solution quality. So a heuristic would do better. So that's why I'm doing like developing a heuristic algorithm, ensuring both solution quality and also improving the runtime as well. So I'm trying to find a sweet spot so I don't lose significant solution quality, but at the same time I have a much closer solution to the central optimization I did at a much faster rate. So that's the only reason from bringing the heuristics. I feel like the proposed control, we solve it using a optimizer simplex, but the structure of the model is very much suitable for solving the problem any other methods. It could be any heuristic at all. So the formulation, like the defining the conflict zone, defining the parameters, this is really helpful for heuristic. And if you observe with the central optimization, we have an updating. So we predict the M parameters, which basically defines the conflict zone. We optimize and we kind of like do a double check there. After optimization, we pass those information, update those M parameter, and again, we do the optimization. If we use a
Great.
more like a calculative approach, we can significantly like we can just simply skip that part. We can because we are calculating everything. We know like where the car probably is gonna be. So that's going to be
Okay.
based on pure calculation.
Great. And based on your early results, if you can share with us, how much did you compromise the optimality when you switched to heuristic, if you can share with us?
Yes, so that's a very preliminary. So I have like checked a couple of numbers. So far, I feel like it's going to be within 5%. Like I have checked the throughput, but for low demand, like 400, it's around in optimization. I think something around, let me see, table. For 400 demand, the throughput is around 389. So there probably I'm going to have like 385 or 386. For the higher demand, this number is going to change, but I'm expecting definitely within 10% and trying to have some numbers within 5%.
Great. And one other question as far as the optimization that you had, the primary was sort of centralized optimization here, which is not really for, it will be very challenging for real scenarios if you want to apply a sort of centralized optimization for vehicles that are approaching roundabouts. Any thought on alternative distributed-based optimization, or let's say consensus-based the planning sort of way that is more applicable here? Any thought on that?
So far I was focusing on the heuristic part first to see like any logic-based algorithm, how much performance it is providing. So I haven't really thought of like distributing it. So I have like thinking of considering like the bandwidth issues or something and bringing those constraints. And that will, from a model perspective, make it a bit complicated. And after that, I'll have to find a better way of solving. So
Is the
yeah,
heuristic approach that you are talking is going to be distributed, or is it still going to be centralized?
I think it can be made distributed. So as of now, it's sort of like a centralized, I would say, but it can be made distributed or parallel. So at first I have to like see like how the algorithm is doing as of now, like sequentially. So after that, I can do some parallelization or something to make it better if requires.
Any thought on consensus-based approaches? Did you explore them?
Not yet. Like, I haven't explored the consensus-based approach with this one.
Okay, great. Thank you so much. That was
Thank you.
all my questions.
Sure.
Any additional questions from anyone? Feel free to unmute yourself and ask freely. All right, I think we're coming to time, but thank you so much. Oh, I think we have one more question.
Yeah, okay. This may be a semantic, but when you say non-signalized versus signalized, okay? But when you're providing all this information from vehicle to vehicle, vehicle to infrastructure, at one point, I think signalized and non-signalized become the same, don't you think?
Yes, that's a great question. Like if we have a central controller there, controller sitting at the middle or somewhere else, so it's sort of like a signalized because it is passing the information. That's actually a good observation. But in practical, we are doing like what Dr. Korimuddin was discussing, trying to do a practical implementation. One of the approaches is like what we can do is using one of the cars, existing self-driving car, and their computation power, and make it as a like a central controller instead of having something in the infrastructure. So one way to do it is to have one of the cars that is going to be working as the like central car or central controller instead of the infrastructure. But your point is right. If we are comparing with the signalized intersection, and if we are bringing a infrastructure in the middle, so it's not going to work if there is a power outage. So we have to have like something alternative. So we can use one of the cars. Like that's the idea so far.
Thank you.
Thank you.
All right, thank you for so much for presenting and sharing your research. We had a lot of like great questions that were asked, and you did a great job of answering them as well. So we just want to say thank you to everyone who was able to attend and come and interact. And we hope to see you at our next seminar.